To understand the basic patterns of soils, we'll start by applying the state factor approach to understanding the controls over soil formation. The authors state that the soil properties of an ecosystem result from the dynamic balance of two opposing forces, soil formation and soil loss. Now, of the state factors that we'll look at, parent material is very important for determining the soils that we have. This here is a very simple diagram of the rock cycle as it was proposed in 1785. So the general patterns of soil formation and factors that give rise to the parent material have been well known for a while. In this diagram, they show three types of rocks. The first is igneous rocks that are derived directly from magma. Second are sedimentary rocks, which are derived from sediments, which come from the processes of weathering and erosion. And lastly, metamorphic rocks, which are igneous rocks or sedimentary rocks, which under either heat or pressure have undergone changes. Now, these rocks get to the surface of the earth and undergo weathering and erosion through processes of uplift. And it's processes of uplift and then weathering erosion that give us the matrix of igneous or sedimentary rocks, as well as metamorphic rocks, and give us the three basic types of parent materials that we'll encounter. Now, the authors state that the physical and chemical properties of rocks and the rates at which they are uplifted and weathered strongly influence soil properties. So the factors that strongly influence soil properties are firstly physical and chemical properties of the rocks. We'll talk a little bit about those later, as well as the rates at which they're uplifted and weathered. Now, the definition of weathering is chemical and physical alteration of rocks near the Earth's surface. We'll talk about what controls different factors of weathering later, but it's important to realize that there's two fundamental aspects of weathering: chemical weathering and physical weathering. Now, Earth's crust cycles every 100 to 200 million years. The crust is very dynamic. There's new crust being generated. There's other crust that is being recycled at the same time. And all of this is associated with plate tectonics. In the book is a really simple diagram of plate tectonics. The authors show a oceanic plate here, the lithosphere, which is being subducted underneath a continental plate. And when they collide, the oceanic plate goes underneath the continental plate, becomes heated up and gets melted into magma. The pressure here from the subduction uplifts material, and that gives us mountain ranges. And that magma that's produced often comes out as lava from volcanoes. So we have a trench, we've got metamorphic rocks that are undergoing pressure and heat, and then we've got mountain ranges and volcanoes at that point of collision between the two plates. Now, this is another diagram showing a specific subduction zone. It's relatively low resolution, I apologize for that. But this is the oceanic plate that's undergoing being subducted under the North American plate, and where that happens we have uplift. So these are mountain ranges right here, and we've got the production of magma that is important in generating volcanoes such as Mount Hood or Mount St. Helens. Now, another state factor is climate, and climate is very important in determining the soil processes and properties that we see. The authors state that temperature, moisture, carbon dioxide, and oxygen influence rates of chemical reactions that govern the rates and products of weathering, as well as biological activity, and therefore the development of soils from rocks. So these factors, temperature, moisture, carbon dioxide, and oxygen, are important for chemical reactions as well as biological activity, and they have different effects on each of those. Now, for biological processes, the CO2, the carbon dioxide, isn't as important, but the temperature, moisture, and oxygen are really important in determining how much biological processing there is of material, and determines the production of organic matter, which is an important part of soils. In addition to think about biological processes, we need to think about the amount, but also the quality of organic matter in soil, and those factors affect both of those. Now also with climate we have precipitation, and precipitation does two things. Firstly, it's going to bring in materials. So we have a cloud, and then we've got rain that comes down. In that rain is water, but there's also other materials that are going to be dissolved in that water, or it's going to bring down particles, for example, and that hit the soils and get deposited here. And so that's a situation where precipitation is bringing in material. But the water associated with precipitation also leaves the ecosystem. And so that means that materials are going to get flushed out of the system. So if we have the soil here and rain coming through, it's either going to run off one way or the other and bring material with it, or it's going to leach out material of the bottom of the ecosystem into groundwater, streams, seeps, things like that. So precipitation both brings in material but also flushes it out. The next state factor is topography. Now, topography influences soils through its effects on climate, moisture availability, and the differential transport of fine soil particles. So when we think about topography, we're thinking about how topography influences climate, as well as the amount of water that's available, and the differential transport of fine soil particles. Now, when we discuss topography and how it impacts soils, now we'll often discuss catinas. What catinas are hill slope complexes. A catina is a fundamental unit of landscapes, and it's essentially this hill slope complex that's going to go from the ridge all the way down to the bottom of the valley. And within a catina, we'll have a lot of different processes that occur that give rise to the different soils that you'll find along the hill slope complex. One of the fundamental things that happen in catinas is that erosion moves finer particles downhill. This is pretty straightforward, but when you have this catina here, for example, this water is going to tend to move downhill, and it often comes out at different parts within the catina, but in the end it's going to end up at the bottom. Along with that, we tend to have erosion moving these finer particles along with water, and that when these fine particles, the weathering happens at the top and at the slopes, they're going to end up here at the bottom. And that's going to give us different soils at the bottom of a catina than at the top or on the slopes. The authors have this figure in the book that shows the catina and what happens in the catina as far as erosion and deposition is concerned. So within that catina, they say that erosion is most likely to happen on the slopes, and deposition most likely at the bottom. And along with that, we find different patterns of organic carbon, both because of the materials that are there, but also deposition of carbon from upland settings. Now within topography, aspect is also important. And what aspect determines is solar input. The further we get away from the equator, the more important aspect is. So in the northern hemisphere, for example, if we have a catina and we have a hill slope, that if the south is this direction and north is this direction, those south-facing slopes are going to get much higher solar input than a north-facing slope. As a result, it's going to be hotter and drier on the south-facing slopes and cooler and wetter on the north-facing slopes. These often warm up earlier in the year than the north-facing slope, for example. And so aspect is important because there are differences in temperature and there are differences in moisture. And again, it's a little bit of a trade-off at certain times of year, in that those south-facing slopes, those that face closer more towards the equator, are going to be hotter, but they'll also be drier. So there's temperature versus moisture differences. In addition, snow redistribution is important within a catina and thinking about aspect too, in that you'll have blowing of snow around and deposition in different places. And the places where snow accumulates, for example, it's going to take longer for that snow to melt, and activity is going to be relatively delayed in the spring compared to other places too. But snow during the winter is often an insulator too, and that's going to extend the biological season, at least for the soils.